So welcome to the next set of lectures for the book Special Relativity, Electrodynamics and General Relativity. This is a course. It's going to be a self-contained course in Classical Differential Geometry for physics students. Okay, so we'll be emphasizing the concepts of Classical Differential Geometry, but our emphasis will be on teaching physics students how to think about the subject and how to prepare for research in field theory, general relativity, and subjects of that kind. So we'll be emphasizing intuition and visualization. We'll be hopefully preparing the students to move on to more sophisticated lectures and textbooks, but this is the intent here, quite focused on understanding the concepts behind general relativity and the differential geometry that underlies it. So we'll be covering these contents. Okay, we're going to begin with just looking at simple things like curves on in flat planes. Okay, we'll understand R2, just Euclidean two-space, and then we'll move on to special cases of geometries. We'll look at the sphere, okay, and we'll discuss some of the concepts there. These are special cases, but they're going to lay the groundwork for theorems of a general variety, for surfaces of general curvature. I mean, the types of problems that we'll be facing in differential geometry and in general relativity. So the concepts will be, we'll first look at general planar geometry, setting the stage. Then we'll look at spherical geometry. And again, I'll be looking at the evolution of the concepts that occur in planar geometry and seeing how they change when we discuss the geometry of a curved surface of constant positive curvature. Okay, then we'll be ready for the general situations, which is curved surfaces. This is classical differential geometry, so our emphasis is going to be on two-dimensional manifolds embedded in R3, in Euclidean space. Now in the textbook, of course, we move on from there to four-dimensional space-time, and we move from classical differential geometry to Riemannian tensor analysis. But I really want to spend some time on this set of subjects, okay, just to lay the groundwork so that everyone understands the theoretical and geometric basis for those more sophisticated developments. So for us, we'll be in the age of Carl Friedrich Gauss, the great inventor of classical differential geometry, and we'll be perfectly happy to understand things at that level. The mathematics that we'll use are the mathematics of vector calculus in 3 dimensions. Later in the course, we'll move on to more modern ways of presenting the material, but not now. I'm not going to challenge your vocabulary of mathematics. We're going to challenge your understanding and visualization of surfaces, curves, and concepts like covariant differentiation, curvature, geodesics, Jacobi geodesic deviations, some of the underlying ideas of differential geometry that find their application in relativity. So planar geometry, spherical geometry, then curved surfaces. We'll discuss the metric. We'll discuss the meaning of the Gaussian map and the Weingarten map, classic constructions of differential geometry. We'll look at the famous Gauss's Theorem Egregium, the excellent theorem, the theorem that shows that you can calculate the curvature, the intrinsic curvature of a surface, just knowing the metric. You don't have to know how the surface is embedded in R3. We just have to know the metric, and from the metric, we can decide on the geometry of the surface in which we might be living. Okay, this is a critical theorem. It's the theorem that led to Riemannian geometry. Okay, now in the websites that back up the book, Special Relativity, Electrodynamics and General Relativity, called the Relativity Doctor, there are 10 supplementary lectures, and they present, for example, the historical lecture and Riemann's thesis to discuss the evolution of the field from classical differential geometry to tensor analysis. So hopefully you'll take a look at that material. After we do Gauss's excellent theorem, we'll move to parallel transport. What is the concept of parallel that generalizes from planar geometry to spherical geometry to general curved surfaces? Once we know that, we can figure out how to differentiate fields which live in the tangent space of a surface, and understand their rate of change relative to the metric of the underlying surface. Okay. After that, we'll be ready to derive the Gauss-Bonnet theorem. Okay, this is the theorem, a global theorem that relates curvature, geodesic deviation to the character of the surface. It's one of the most significant results and theorems in mathematics. It's the theorem that led us from local differential geometry to global topological geometry of surfaces, and we'll prove it, derive it in this course, and we'll see that the idea of it goes all the way back to planar geometry, asking the question of how the tangent vector to a closed curve changes as you move around that closed curve. The turning angle of a tangent vector to a closed curve. Simple concept in planar geometry. A little more challenging in spherical geometry. We'll demonstrate it for spheres. Okay, and then we'll turn to the general case of a curved surface and see how the idea of a turning angle, okay, gives us the Gauss-Bonnet theorem. Okay. Once we have the Gauss-Bonnet theorem, we can discuss geodesic coordinates. We'll be discussing the generalization of what does it mean for a straight line in planar coordinates. We know that concept. We know how to use straight lines to construct triangles. We know the geometry of triangles in flat space. We'll generalize those ideas to geodesic triangles on the sphere, and then we'll generalize those ideas to geodesic triangles on a curved surface. In that way, we'll understand the Gauss-Bonnet theorem and move to Gaussian coordinates and discuss other properties of curved surfaces like the geodesic deviations and Jacobi fields. Okay. At that point, we'll try to consolidate all of our knowledge, okay, and discuss the relationship between parallel vectors, parallel transportation, covariant differentiation, and Gaussian curvature. Put all that together and discuss curvature and holonomy. Okay, we'll have a few words to lead us to the next level of the course, which is Riemannian geometry. But we'll take a look and have an overview of classical differential geometry at this moment. Now, this set of lectures is going to follow very closely the supplemental lectures to the textbook Special Relativity, Electrodynamics and General Relativity. In particular, there's this supplemental lecture number 9, 65 pages of Classical Differential Geometry. Okay, and I'm going to follow that rather closely in this set of video lectures. Okay, now if you have a PC with a large screen, you can blow it up and read easily all of the posters that I present here. If, however, you're stuck on an iPhone or a Galaxy S9 or something like that, you're not going to be able to read these posters. But the solution is make yourself an electronic copy or a physical copy of Supplemental Lecture 9, and that'll take you through this course. Now, there are other supplemental lectures as well, and when I use them, I'll also reference them so you can follow along. Okay, so that all the formulas that I'm putting on the posters are presented nicely typed, okay, in LaTeX, okay, with good figures in those documents, and we can all follow along rather easily. Now, after we finish the material in Supplementary Lecture 9, we'll do some special topics. Okay, I'll want to look at non-Euclidean geometry. So I want to look in more detail at the geometry on a sphere, and we'll discuss the projective plane. Okay, the sphere with antipodal points identified, and discuss the geometry of a space of constant positive curvature, a symmetric space. Then we'll turn to the case of hyperbolic geometry. That is the case of a surface with constant negative curvature. In that case, we'll go back again to classical differential geometry, okay, and discuss the Poincaré disk model and the upper half plane model of hyperbolic geometry, the geometry that underlies the work of the originators of hyperbolic geometry. So that'll be quite interesting. We'll have illustrations of geodesics, okay, of hyperbolic lengths, of hyperbolic triangles, of the Gauss-Bonnet theorem, all within this context, which is very easy to illustrate and has a minimum of technology lying between us and the construction of the geometry and the results. Okay, then we'll turn back to curves and three dimensions. Okay, in the presentation that we'll do here, based on Supplementary Lecture 9, mostly we'll spend on curves that are embedded in two space, either in a flat plane, perhaps on the surface of a sphere, or perhaps on the surface of a general curved surface. But there are things to be said about curves in three dimensions, which we'll like to talk about. Okay, how do you measure the various curvatures of curve in three dimensions so that you specify it uniquely? Okay. Okay, we'll do the Gauss-Bonnet theorem here for whole surfaces and for regions, curved regions inside a simple connected curve. But there are other applications of the Gauss-Bonnet theorem to triangulated surfaces and global topology, and we'll deal with them in a special lecture. So we'll have some special lectures at the end which look at these particular topics. Okay, now I should say that each lecture is approximately 30 minutes long. Some of our topics are too long for 30 minutes. We'll have a part A and a part B. Okay, and they'll be labeled on the YouTube site appropriately. But I think 30 minutes is good for us because you have other things to do. 30 minutes is a good bite-sized bit of mathematics, a good bite-sized bit of the time that you have, and maybe we can make progress that way. Now let me just say a few words about the underlying references for the course. You'll see that there are references in all of the supplemental lectures, and I do want to point out a very special one, and that's our major reference in Classical Differential Geometry, which is the outstanding textbook of Manfredo P. da Como the great Brazilian educator in differential geometry. Okay, so you can find that book available on the web, and I strongly recommend that you take a look at it, and that you buy it either as an electronic version or as a paper version as well, whatever, because it's really an outstanding textbook. It's just gets to the heart of the matter with just the right amount of formal mathematics. It's wonderful problem sets, wonderful illustrations, and apparently I can't say enough about it. Okay, so let's begin with an introduction to planar geometry. Now look, this is going to look really simple, and a lot of people are going to say, ho hum, I know all this. This is to set up the problems for later developments in spherical geometry, hyperbolic geometry, and general curved surfaces. So bear with me. It's going to be deceptive. Okay, I'm going to introduce simple ideas, but these are the simple ideas which are going to generalize to the general curved surfaces and lead us to very non-trivial ideas in holonomy, covariant differentiation, Gaussian curvature, and Gauss-Bonnet theorem. So be careful. Okay, be careful. Okay, so we'll consider an xy plane. I'll call it R2. I'll abbreviate that all the time because I don't want to have to say that all the time. Euclidean, it's flat. We know all about it. I'm not going to review it. The first thing we want to know when we're facing a new space, however, is to ask, what are the symmetries of that space? Well, we know the symmetries of good old xy plane. There are rotations and translations, for example. And these are symmetries because they preserve distances and angles. If I construct an object in 2 dimensions, I can rotate it, I can move it, okay, and it remains the same. Okay. The action of moving it preserves distances. If it preserves distances, it preserves angles. Okay, angles are defined by distances, by the law of cosines, for example, and so I know the symmetries there. There are other symmetries as well, but for the most part, these are the ones I'm interested in. The symmetries that are continuously connected to the identity, rotations and translations. There are discrete symmetries as well. I don't think we'll be using them, so let's just emphasize what we're using. So there are curves of various types. There are straight lines. Okay, so there are straight lines. Shortest distance between any 2 points, a straight line. We call it a geodesic. We want to generalize that concept to other manifolds, 2-dimensional manifolds that might be curved. We have curved lines as well. We want to understand what a quantitative measure of the curvature of a curved line is, to visualize it and to quantitatively understand it. We'll have curves which are simple, regular, and closed, and I've indicated one here. Simple, so it doesn't intersect itself. Regular, it's nice and smooth. Closed, well, it's closed. Okay, we'll have curves of that variety. We'll also have closed curves which are only regular in sections. Okay, so they might be like this. Okay, a piecewise smooth curve. So it might have vertices. Here's one that I've imagined with 3 vertices, and I've labeled them with these appropriately. I've given the curve a direction. I sweep through it in that way, and so I might call that the positive direction, and the other way, negative direction. Well, I make conventions like that as we go. That will be useful because I'll want to discuss oriented curves and oriented surfaces, and I'll want to relate oriented curves and surfaces from one manifold to another. Okay. Well, in R2, I know how to do the geometry there. Let's just illustrate a few things about the geometry. I can set up an x and y plane, x and y axes. I can make them orthogonal. I can make unit vectors in the x and y direction in the usual way. I'll put a hat over over the symbol to indicate a unit vector. It has a unit length. Sometimes I'll put a squiggle or an arrow over it. I'm not going to be terrifically consistent about those things, but I think that the notation will be clear enough. And then the length, the inner product of one of these fellows with itself is 1. I dot product with j is 0. They're orthogonal, and I'm presuming that we all know the geometry of 2 dimensions. We all know dot products. We all have a background in vector calculus. That's a prerequisite for this for the course. So, for example, an example of a closed curve might be a circle. Here's a xy plane with a circle of radius b. I label the point P on the circle with an angle theta, and so the x coordinate is b cosine theta or cosine t. T might be a parameter which measures, okay, how far along this curve I've gone. We're very familiar with the angle theta. Well, the angle theta I can take as the ratio of the arc length off the x-axis to the point B divided by the radius b, and I'll be doing that time and time again. Okay, in this case, t might be that, or might be something different. Well, I have a lot of choices as to how to parameterize my curves, but I have in mind, of course, an invariant geometric construction which can be described in many ways. And here's R. There's a tilde under it to indicate it's a vector in 2 dimensions. So it has an x component and a y component like that. If I use the conventional theta, it runs from 0 to 2 pi. Now, one of the most convenient parameterizations we're going to have, and we're going to use it time and time again because it makes the mathematics as easy as possible, is the arc length. Okay, well, in the case of the circle, we use the arc length as the parameter. Well, theta is just arc length divided by radius. So if the radius is 1, theta is just the arc length. Theta is just a distance. It's an angle, but it's also a distance if we restrict ourselves to circles. The arc length is a good parameter for curves. We call it S. In this case, S is b, the radius times the angle theta. Well, in general, for a general curve, what's the arc length? Well, the arc length is you just add up infinitesimal bits of dr along the curve and integrate them up. So I write the magnitude of r prime, where the prime means differentiation with respect to the parameter. And then I take that magnitude and multiply it by dt. So as you see, dt here, canceling the dt and the r prime, means I'm just adding up the magnitudes of dr as I move along the circle. And that's the arc length. Sure, that's the arc length. Easy to compute in the case of a circle, harder to compute in other cases, but it's an awfully good parameter because it tells me where I sit on a general curve. So here it is. Now I'm going to use this terminology of r prime to indicate differentiation with respect to the parameter t. Okay, so that's what the prime is going to mean in most of the cases that I write it down. Sometimes in the textbook we would write r dot, and the dot meaning a differentiation with respect to a parameter. For the most part in these lectures I'll use a prime instead. Okay, and so here's r prime, and here's the magnitude of r prime, just a square root of x prime squared plus y prime squared, just writing down the Pythagorean theorem. Okay. Well, if this is the arc length, then by the fundamental theorem of calculus, the rate of change of the arc length is just the integrand, and so I write that down. Okay, so the speed. Well, so now it's natural. Being a physicist, I might try to put a little color into some of these equations, and I might think of t as being time. Well, if I do that, then ds dt is just the speed, okay, and the speed is just the magnitude of the velocity. Okay, and that just then illustrates to me the construction of the arc length. And we're going to use it again and again and again. And if we're not going to be using the arc length, then it's just going to be a question of changing variables to get to the other variable that we might want to use. And the exercise of going from arc length to a different variable might just be an exercise in the chain rule. And we'll do that when we come up against it. Okay. But we'll see that the arc length has very nice attributes that make the formalism quite handy. Okay. So use S, the arc length, to parameterize a curve. And why? Well, because then the speed is 1, right? The speed is 1 because the rate of change of the distance divided by the distance is just 1. Okay. Okay. So that's okay. So that's an obviously nice point about it. If you look at the rate of change of distance compared to the distance, then of course the speed is 1. Okay, and so that's handy. And then in addition, we get another good property of using the arc length as a parameter, because if this speed is always 1, okay, then r prime dotted into itself is 1. Okay, for any s. In other words, if I differentiate that with respect to s, I have to get 0. So that means that the r double prime dot r prime is equal to 0. Just differentiating this thing, right? On the left-hand side, I'll get twice r double prime dot r prime, 2 terms. On the right-hand side, I'll get 0. So I learned that this dot product is 0. In physics terms, I would be saying that the acceleration is perpendicular to the velocity if I use the arc length as my measure of time. Okay. Okay. This type of an identity, it's trivial, it's simple, it's going to come up a lot in classical differential geometry. Just remember it. Okay. We're going to construct many vectors, okay, which are normalized to 1, or might be orthonormal to one another, or something like that. We'll have a relationship that a vector dotted into itself is a constant, or a vector dotted into another vector is a constant, which might be 0. In which case we'll differentiate those expressions and find that something that looks like an acceleration dotted into a velocity is 0, and that will be important in our logical developments. Okay, so it's trivial, but keep it in mind. Okay, lots of examples. If you take a ball and you on a string and you whip it around your head, then of course you know that the acceleration is centripetal, the velocity is tangential. Okay, and so r double prime dot r prime is equal to 0. Okay, so so there's an illustration of it, but the fact is that this is generally true as long as I use arc length as my parameter. I don't need to specialize the circles or anything like that. This just follows from the fact that my velocity is 1 if I use arc length as a parameter, and then I get that the second derivative of the vector dotted into the first derivative is equal to 0. Okay, and so that sets me up for the idea of acceleration. Acceleration is perpendicular to the velocity locally, and here I simply illustrated it for a general curve. For a general curve, I have R of S, I have R prime of S, right? R prime is the rate of change of R with respect to S. It's a vector. It's clearly tangent to the curve. Okay, and then R double prime is perpendicular to the tangent. So I've drawn it in this direction because R is bending in that direction. So if I have a numerical example, R double prime would point positively in that direction. And R double prime indicates how quickly the curve deviates from a straight line. Okay, so the magnitude of R double prime is by definition the curvature of the curve at S. Okay, and so let's stop here and then pick it up next time and try to develop the quantitative concept of the curvature of a general curve on the basis of its second derivative and define the curvature parameter kappa, and learn a little bit about the geometry of curves in R2.